Well, my mind, and when I talked to some of the executive, we thought of Sandy Ikes. Having seen her present many times at Science World, I've also seen her present with her dad at STAO. I knew she had the exact qualities we needed to provide. She's fun, she's entertaining, and she has some very great science demos. So I'd like to introduce Sandy Ikes. Thank you.
It's a real pleasure for me to be amongst so many fellow science geeks, science teachers. Among other things, I don't need to work very hard to convince you of a few things. I don't need to convince you that hands-on activities are a really good way to learn. I don't need to convince you that there's some really neat stuff you can do with high tech, with iPods and iTouches and smartboards and what have you. I don't need to convince you that, well, I did this morning, so I don't need to convince you anymore, that carefully planned discrepant events are a really great way to learn. And I don't need to convince you that field trips are a great way for students to learn. You know this stuff. What I would do for the next little while is I would show you some of the things that really remind me how much I love science, and probably mostly physics, because that's my background. Despite the jitters, I love playing. And I love playing when there's lots of people to watch me play. I mean, what a good job is that? What an awesome job. But partly it's also because I think that if you want to find one thing that distinguishes an excellent science teacher from a really amazing science teacher, the one thing that might distinguish those people is that the really amazing science teacher hasn't forgotten the fun of learning new stuff, and hasn't forgotten the fun of being curious, and is maybe a curious learner themselves. But we're going to start, I'm going to invite you into my shower. Now I know that's a bit weird. It involves no nudity. I just want you to visually imagine yourself in the shower. You're enjoying the hot spray. It's terrific. It's terrific. And all of a sudden, that bloody shower curtain, it comes in, just when you're covered in suds, it comes in and it wraps yourself right around your middle. It's like, look, that shower curtain, go away from me. Who's had that happen? Right. Okay, so normal people buy those glass doors, or they put magnets on their shower curtain. Normal people do that. Physicists go, ooh, Bernoulli's principle. Bernoulli's principle is at work in my shower. And Bernoulli is quite fun. So Bernoulli, in case anyone needs to sort of catch up with me here, I mean, we talk about it a lot at Science World, but I have to say it wasn't part of my physics-backed education at all, is the principle that faster-moving fluids exert less pressure. So the faster-moving fluids inside your shower are less pressury than the still air inside your bathroom, and you're plastered with a shower curtain. Now, since I couldn't bring my shower with me, I brought the next best thing. I brought a roll of toilet paper and a leaf blower. Okay, so Justin, your job is going to be to hold a roll of toilet paper, which I have cleverly attached to a paint roller, because isn't that what we all do with rolls of toilet paper? Your job is going to be to hold that nice and straight out that way. Awesome. Now, in order to do, you know this thing, right? This, you know how it lifts? Fast air, slow air, so it lifts up a little bit. Right, so we're going to do that, only I don't have enough hot air. You might be doubting that. I don't have enough fast air, so I'm going to use the fast air from a leaf blower. And just to prove that it's fast air coming out of the leaf blower, fast air. Fast enough. All right. That also proves that it's plugged in, which, you know, that sometimes happens. So what I'm going to do is I'm going to direct a stream of fast air over the top of this leaf blower. Fast air, slow air. We kind of expect this to go up a little bit. Are we good with this? Okay, are you good with this?
I hope so.
Okay, if you raise it up a little bit, I might have a better go here. All right, here we go. And a 1, and a 2. Here it comes.
Cheap, but not that cheap.
Your prize for participating today is a whole lot of toilet paper. Give Justin a big round of applause. Go to the kitchen, because the kitchen is actually a really good place to get curious about how things work and why things happen. I get curious about things like induction cooktops. I'm really, really curious about how bread works. Being not a biologist, bread is really, really cool stuff. So there's lots of good stuff you can do in the kitchen. Now, I like to do physics with my breakfast, and I've been curious about something. So I've got some, well, they're not Cheerios, they're multi-grain, organic, blah, 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 adjective, oats. And I have a small daughter, and you can't have like boring Cheerios in the house. I'm going to put the Cheerios into my milk, and when I've got down to my last few Cheerios, let's see if we can see what they're doing here. I'm going to focus on the Cheerios and not on the thing that says Pyrex. They exhibit a very strange phenomenon that has been dubbed Cheerio magnetism. They're Cheerio magnetic to the wall of the container. But isn't that weird? Like, why should Cheerios stick together, right? I mean, I don't know, maybe it's the iron, the fortified iron in the cereal. It's not. I don't think it is anyway. I don't think there's enough iron in this stuff. But they're sticking together, and then they stick to the side. which strikes me as a very strange thing. And in fact, it struck some people, some other physicists, as a very strange thing. And so they did a little bit of experimenting with bubbles and things that are a little bit heavier than water but will sit on the surface tension, and things like Cheerios that are nice and big and obvious and float. So the Cheerios are in fact floating, they're less dense than water, and there they are sitting on the water. And I mean, you know what's happening at the edge, where the water meets the edge? Yeah, everybody's doing this kind of thing, right? There's a meniscus because the water adheres up the side of the container. So there's a little hill, an itty bitty little hill, whoop, right up to the side of the container. And so the floating Cheerio is experiencing the force of buoyancy. And I'm feeling very self-conscious about anthropomorphizing the Cheerios. So I'm just going to, I'm going to put that out there, take it for what it's worth. All right, the floating Cheerio is floating around, it's experiencing the force of buoyancy. Buoyancy is pushing up, whoop, and along comes the Cheerio, and look what it sees, a little hill, and on the upside of the little hill, that's more up than the downside of the little hill. So it actually floats right up the meniscus. Oh, that's cool. So that's why if you look at your glass of champagne, the bubbles will often go to the side, right? And that's why they're floating up that little hill of the meniscus. But the other thing that's weird is that each little Cheerio has a little hill around it. They're like little volcanoes. They're a little crater on the top of the volcano. They've got a little meniscus coming right up the edge of the Cheerio. So another Cheerio comes along and goes, ooh, I'm going to float up your hill. And they hook up together. So you've actually got quite a lot of physics going on, and a lot of really weird science about how water interacts with other stuff. So that wound up being the subject for the preschool science program, along with a lot of stuff about things that float and things that sink. So I have here it's actually a super cute little can of Diet Coke. It works, what I'm going to do is, works actually with the big cans too. Never tried it with bottles, but it works with the big cans too. But I thought, isn't that really cute? And it floats. Awesome, so we can say that's less dense than the water. Kind of funny, because it's mostly made of water. Now I've got something similar here. Something similar, same size, same shape, same volume. I can prove this to you. Same volume. Okay, I put this one in the water. Curious. Very curious. So one floats and one sinks. It's because that one's been on a diet. That's why it's called Diet Coke. Okay, maybe this one's kind of freaky and they underfilled it. Or maybe something else is happening. What else could be? What else is happening? It's all about the sugar, right? So it turns out that aspartame, you need just a tiny, tiny little bit to be as sweet as the multiple tablespoons of sugar that go into here. Sugar is a lot heavier. Well, you need more of it, so that one is actually heavier. And so it's a pretty cool demo, right? Because you can talk about density and all kinds of things. But here's a way you can make it even better because you have more than center stage to talk to your students. You could actually weigh a bunch of these cans. You could weigh a whole bunch of Coke and a whole bunch of Diet Coke. You can figure out what the tolerance is. Like, are all the Cokes the same weight? How much is the tolerance? Good to do that yourself before you try this, because occasionally you get a freaky Coke or a freaky Diet Coke. Okay, so good to test it out yourself. So I've been playing around with this, and my daughter, who's 7, discovered this one for me. I didn't know I actually had this demo. So I have a white rock, not the city, and predictably the white rock sinks, and I have a black rock, it is a rock, and perhaps unpredictably, the black rock floats. It's amazing the kind of science you can do in the bathtub, or the kitchen sink, or the beach. Okay, am I cheating? Who thinks I'm cheating? Who thinks I'm messing with your head? Well, what's the black rock? Hummus. And you know, a long time ago when we were doing these water programs, I actually ordered huge chunks of hummus for great amounts of money. And this was actually sold in a drugstore for cleaning up feet. So I fantasize about creating the unspillable cup. no more milk all over the table. I'm going to make an unspillable cup. The problem is that in order to drink out of a cup, it has to have a hole. And there's lots of funky technology for sippy cups that prevents water from coming back out the hole. Also makes them darn hard to drink out of. So I was getting kind of curious about how some of these things might work. And I got a cup. And I thought, well, what have I got hanging around? I have orange cards with dots on them. Don't you have one of those? Okay, well, all right. So I have orange cards with dots on them. And I thought, well, maybe that would be a good lid. Well, this is, you know, this is kind of tame. I need to up the level of anxiety a little bit. So I need somebody to help me. And the person I need, you lift your hands, you might get volunteered. The person I need is right there wearing green. Yep. Okay. I'll give you the hat of science. This is Lisa, everybody. Lisa is going to be the tester. Aren't they wonderful? We've got fans. I'm so glad. Okay, Lisa's going to be the tester for my unspillable cup. So right now it's not spilling because it's right side up. But we have to test it with the upside down part and see whether my fancy lid is going to keep the water inside. Is there water in the cup?
There is water in the cup.
There's water in the cup. Is there the potential that Lisa is going to get very wet doing this? Oh, yes, there is. Oh, yes, there is. Okay, so I'm going to turn it upside down. Okay, now, force pulling down? Gravity. Is it pulling the water? Is it pulling the card? Is Lisa frightened? Oh, she should be. I had too much coffee, my hands are shaking. Oh, look at that. You want to look up there, Lisa, and see what you got? So, I have invented the unspillable cup. The only challenge is that I'm not quite sure how I'm going to get the liquid out of that to drink it, even though I've got a super duper lid and a lot of help. Something must have been holding the lid on. Shout it out for me, you know what it is. What's holding the lid on? Oh, I can't hear you. Air pressure, yeah. So, it's often a little bit counterintuitive that air pressure pushes up, but it does. It pushes up, sideways, down, every direction. Lisa was totally confident that it was going to push up for her. Give Lisa a big round of applause for taking it up. Change things up a little bit. So I went to the hardware store. It's going to be hard to see because it's full of holes. This is screening like you use when you're fixing your screen door. And I'm going to fix it on there really well, so I don't have any weird accidents. Now, this is great because it's got tons of holes in it, right? So water can go in and water can come out. So here goes the water in. And here comes the water out. Excellent, a cup we can drink out of. So now we have to test its unspillability. And I need a helper. And I think my helper is wearing blue there in the second row. Come on up. Come on up. I know, you just happen to be sitting in front of my other helper. Okay, what's her name? Erin. Erin, you're going to wear the hat of science. And we are going to test the unspillability of my unspillable cup. So, let me see how we got here. Don't look back. Whatever you do, don't look back. Remain exactly still. Water goes in. Water comes out. Good, I can still drink it. Okay, so water goes in. All right. And then here we go. Oh, look at this. Wow. An unspillable cup that you can drink out of. Just stay there, stay there. Because those people out there, they don't believe me that there's water in there. They think I've done some kind of a weird trick. There's water in there, isn't there? Yeah, there's real water. Oh, there's real honest to goodness water in there. What on earth is keeping it in the cup? Sheer willpower from my volunteer. Sheer willpower. Yeah, no, a little bit of Hogwarts magic. No, not any of that. And it's, woo! You did a great job, Erin. Give her a round of applause. So it's a fun combination of the adhesion between the water molecules and the little squares of the screen. So they grab on little squares of the screen. The water molecules are coherent with each other. They grab onto each other. Plus, if I hold it right upside down, I've still got a little bit of help from air pressure pushing up. So there's a lot of interesting stuff going on with that, with my crazy that I stole from my kid today. I stole from my pets. This is a cat water dish, okay? And it's really simple. It's like a screw-on lid thing and a blue tank thing. And you fill the blue tank thing with water, right? And you actually it doesn't have to be super full. You screw on the lid. Now, once again, the poor cat, right, it's a lid. The cat can't open the lid to drink. So we have to find some way to let the water out of that. And honestly, when I saw this the first time, I thought, well, I think I know the physics, but I really don't believe this is going to work. We're going to turn all this water upside down. In the other side, there's a wee little dish. Maybe holds a half a cup of liquid. And that's a lot more than that. Yeah? So we're going to turn it over, and we're going to hope that the floor doesn't get wet. You know, I'm a physicist, but I did this over the sink when I first bought this thing. And it goes glub, 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 and you can see that the water's coming out. And it's coming out, and it's not even full on this side here. You can tell me, Sam, how much water's in there? Oops, I'm going too far. How much water's in there?
Oh, half a cup.
Like maybe, yeah, it's maybe half full. Isn't that cool? So somebody else beat me to it and invented the unspillable cup. So there's pressure pushing down here and holding up all that water. Of course, as water disappears from the side, this thing will lose water to equalize to make the volume in the side what it used to be. So you got pressure pushing down here, and the pressure inside here is reduced as the water comes down to the point where this pressure is enough, the difference in pressure is enough to hold up that much water. So, look at the funny places you can find physics. You can find physics in the cat dish. Now, if somebody can find me a way to be productively curious about the cat litter box, I'm trying to prove to you that the curious mind can find curiosity everywhere. And one of the things you find everywhere in Vancouver are these, paper coffee cups of assorted sizes. And there is amazing physics that you can do or discover or play with these coffee cups. So one of them that I rather like, this demo has mysteriously disappeared. One of them that I rather like is to take two of them together like this, and then you've got a bunch of rubber bands strung out in a string, and you pull, and you wrap. I know this is very difficult to see what I'm doing. Oh my goodness, you're brilliant. Give Marvin a big round of applause, he's awesome. All right. And now I'm going to launch this, not at myself, but out towards you. Now, because I'm going to pull it back and let it go this way, all that elastic potential energy is going to fling the cup towards you. It's also wrapped around, so it's probably going to twist the cup. We can hope anyway. And some of those forces will go into play into making this do what it might do. Pretty cool, eh? Flying machines in the coffee shop. So your local Starbucks will be glad to have an invasion of physicists or scientists of all stripes. See, the bottom edge of the cup has to be pushing away from the direction it's going. So the bottom edge of the cup is actually twirling this way as the cup is moving this way. Sorry, that's moving along with. What am I doing? Yeah, it's moving, it has to be moving along with, and this one has to be moving back, okay? So the bottom edge of the cup is moving forward as the cup is moving forward. The top edge of the cup is moving backwards. Now, here's where things get a little weird, because it's of course the cup moving and not the air. But let's sort of sit on the cup for a minute and pretend that we're watching the air come by. So here comes the air towards the cup, but the bottom edge is shoving forward. So it's slowing things down here. That's where the slow, turbulent air is happening. Up top here, where that edge of the cup is coming along with the air, you're actually pulling some air along and making it fast up there. So we've got fast air, slow air, just like the toilet paper. You've got something that kind of flies, or at least sort of floats in the air and gets a little. So these things, it's a huge waste of paper, right? These are the things that go around the coffee cups so that you don't burn your hand on them. But they have kind of an interesting shape that has kind of an interesting property. And so I'm going to put them up here. And I had to rip them a bit to fit them on the overhead. So it turns out that, yeah, one of them's a bit longer than the other. Yeah? Which one's longer? The one on the left, right? So, okay. All right, so it's the one on the... Okay, which one is... Which one is longer? Yeah. Which do you think? They're both the same size. The young man in the front row says they are both the same size, and in fact, if I put them on top of each other, you can see that they are both the same size. So something weird is happening there, and it's not something I'm doing, it's something your brains are all doing, which is comparing the long side of the one to the short side of the other, and just overloading with the complication of trying to calculate those many things at once. It's a pretty funky optical illusion. You can order these little curved thingamies from your handy-dandy science supply store for $15, or you can pick through the garbage and get Starbucks sleeves. So thank you, middle school teachers in Chilliwack, for saving us all a ton of money. Part of my job involves watching people learn, which you have to admit is a tricky business, right? I have to sort of guess whether my lessons have been successful. And my lessons are usually contraptions that people come and play with. And they're not thinking, oh, I'm at school, I better take notes. And I can't give them a test at the end of the unit. They think I was nuts, right? I'm sitting out there passing exam papers out of the exit science world. It's just not going to fly. So what I actually do, and I'm not kidding you here, is I hide behind the pillar and I watch them. Now, I can't get in their heads, so I don't know which neurons are connecting to which neurons. I have to infer based on what they are actually doing, which is science, actually, so that makes it quite entertaining. And I have to say that all of that, despite the fact that it's kind of complicated and time-consuming, it's way more fun than marking. Beats marking, hands down. So I sit there with my clipboard and I watch for behaviors. Right? Because the only way I can tell what people are doing is by looking at what they're doing. I don't know what they're thinking about. So I look for behaviors. I look for behaviors like, tries the thing again and again. You know, can I lift the hippo? Can I still lift the hippo? Well, we have a lever that lifts the hippo. Can I still lift the hippo? Okay, if I move the rope, can I lift the hippo? Aha! Now they're taking charge of their own learning. Isn't that cool? So they move the rope, now they can, and they can't lift the hippo. Okay, then I look for things like calls other people over to join. Okay, so we had an exhibit called Grossology. We had a thing where you could squeeze bottles and you could smell gross smells. So that was a really fun one because you get some kid going, hey, Mom, come on over here, you gotta try this, right? Well, I mean, aside from playing a joke on Mom, that's all about sharing what you've got, so you've got it and you own it, and now you're gonna share it. So we look for that kind of behavior. Sometimes you can hear what people say, sometimes they say, hey, that's just like when I use a leaf blower and toilet paper at home. People are truly wired up to learn, and if you've ever watched a baby learn about gravity, you know they do science before they can talk. And it goes something like this. Pick up the stuffed bunny, drop it off the change table. Pick up the block, drop it off the change table, it falls. Pick up the wipes, drop it off the change table, watch Mommy scramble around for it. Pick up the diaper, drop it off the change table, watch Mommy have a heart attack. Okay, so all that repetition, that's experimenting, changing the variables. You've learned that everything falls. You know that everything falls. So if I'm going to get you excited by falling things, I have to do some weird stuff. So one weird thing that could fall is a very, very, very long string of beads that was intended to decorate probably what must be the largest Christmas tree in the universe. Though I bet I could make this bigger if I tried. It's in a cup, and it has a little end sticking out. Come back here. And as you can see, these are animated beads that are desperate to escape their confinement. Somebody put a hex on them before I left. Okay, so if I pull a little bit of this out, gravity is pulling on it, and just like the baby drop in the diaper, or the wipes or whatever it is, you know that gravity is going to pull these beads down. Now the funny thing about this one is that each bead is attached to another bead is attached to another bead. So they're all kind of entrained to come along with it, right? The other funny thing is that as more beads come out, you've got more weight falling. So that's also kind of an interesting puzzler, what happens with that. So usually when you drop things, it's the one thing and it falls, and we all know that G is constant and all that good stuff. But here we're messing it up by having this long string of things. So this doesn't last very long, usually. So watch carefully, I'm going to drop something weird. Hey, I dropped it and it went up. How cool is that? Isn't that fun? So I was looking for more things to drop. So I thought about slinkies, right? Slinkies, everybody loves a slinky. How can you go wrong with a slinky, right? So I thought about dropping a slinky. So I've got a short slinky and a long slinky. And what I want you to look at are these little green blobs of tape that I've stuck to my slinkies. One is up here at something higher than 5 feet off the ground, but not much. This one over here is a lot closer. That's almost below my waist level, maybe. Okay? So, yeah, you can stand up if you can't see, that's okay. I can only get so tall. I'm kind of a shrimp. So, what I'm going to do is I'm going to drop these two things. Now, if I were to drop a little ball and a big ball, like, Galileo is said to have done, they're going to hit the ground at the same time because I'm going to drop them from the same place. But here, now I've got something weird going on here. This one's actually way lower, right? This one's, and it's long. So you'd think that this one's going to hit the ground. This one's going to hit the ground first, yeah? Okay, here we go. I'm going to drop them. And because you may not be able to see, I want you to listen for the bangs, okay? Which bang comes first? Oh, stop bouncing, Slinky. That's kind of like telling grade 8s to stop bouncing. Okay, here we go. 1, 2, 3. How many bangs? One bang. They fell at the same time. Okay. So, this time, because most of you were listening, this time I'm just going to drop this one, because really this is the one that should have hit first, because it's much lower to the ground. So I'm going to drop this one, and I want you just to watch the green blob, okay? And I want you to watch it fall to the ground under the force of gravity, okay? I'll do this a couple times even. Here it goes. Whoa, anti-gravity! Did you see it hovering there? Okay, one more time. One more time for the record. Long slinky. Stop bouncing. Watch the green ball as it hovers in midair. Oh, I haven't let go yet. Okay, here we go. Cool. So that's quite strange. And I mean, this was a new discovery for me like last week. So I thought this it hovers in midair, don't things fall? Well, and I sort of expected the whole thing to fall according to its center of mass. But of course, what you forget, or what you're carefully led to ignore, is the fact that the slinky does that the minute you let go of it, right? There's a spring factor happening. So the slinky actually compresses up and then falls. And for a pretty close approximation, but not a perfect one, it's as though this bottom doesn't move at all. Well, to a pretty close approximation, it doesn't move, unless the slinky has time to do some of these things. Now, if you want to see this done larger than life, YouTube falling slinky, people have been dropping them off office buildings and bridges and all kinds of wacky things. See, I mean, who drops slinkies off a bridge? A curious scientist. Hey, I have here a glass of water with no unspillable cup on it. I have here a cake pan, square, 9 by 9 inches. Beats me what that is in centimeters. I'm also feeling self-conscious about that. But I don't know if it wants to be here or not. Okay. And on top of that, I have a little tube. This could be a toilet paper tube. It's a piece of PVC pipe. My family is strangely enamored of PVC pipes. Right? Oh, ABS pipes, I'm sorry. Okay. Now, this is a foosball. Nobody's emotionally attached to a foosball, I hope. This, on the other hand, this is an egg. It is a raw egg. Okay. Let's just take a minute to sum up some of the forces that are happening here. Forces on the egg. Gravity down. From the tube. The tube, normal force pushing up. Okay, good. Forces on the tube. Gravity, normal force of the pan. Forces on the pan. Oh, gravity plus tube plus egg. Cup coming up. Okay. Cup, all those other things, and table. Water, cup. More or less. Okay, we got it more or less. So we know where the forces are. They're all beautifully in balance. So what I'm going to attempt to do is remove some of these objects and see what happens using the force of gravity. So I'm going to attempt to remove the cake pan and the tube, like this. Okay. I'm going to attempt to remove the cake pan and the tube by exerting a very strong force on them. Notice that I am being very careful to center this. Maybe the most important part of this demo. Okay. And the force I'm going to use is F broom. F broom here. All right. And brooms have quite a lot of elastic force if you do this. They have a lot of elastic energy, and they move that way really fast. So I'm going to move this broom super close to the table. I'm going to hope very much, very, very hope, that the broom hits the plate, the cake pan. I'm going to hope that the cake pan goes in that direction, because that's where the force is going. I'm going to hope that the cake pan pulls the tube, leaving this poor innocent little egg unsupported, except that there's a glass of water under it. So that's what I'm hoping is going to happen. This is a kind of a fun demo because if you do it right, everybody's really impressed, and if you do it wrong, everybody gets a really good laugh at a broken egg. Okay, here we go. And a 1, and a 2, and a 3. This last one is kind of a gratuitous demo, but I figured that after a long weekend of being, or a long 2-day weekend, of being bombarded with cool ideas, you may need to have a party. And so I'm going to show you a demo that plays really, really well at parties, and might make you curious or emotionally engaged. And I'm going to need a couple of people who don't have balloon issues to help me with this one. If you have, I will use you guys, but I need some big people that don't have balloon issues. 1 big person, 2 big people with no balloon issues. Excellent. Trust me, if you had balloon issues, you would know. They make some people break out in hives, and they make some people very frightened. So your first job is to take this very large number of balloons and put them on this towel. Okay? Can you manage that? Right now? Yeah, right now. Put them on the towel. I'm just going to improve the visibility here a bit. No, it's not an ice demo unless it involves throwing water on the floor. Now I know that you all have one of these in your closet. Yeah, isn't that fun? This is my mom's contribution to this conference. This is just a big plywood board. This could be a table, but I never know what I'm going to get for a table, so I carry around a big purple board with me. What we are going to do is on these delicate, breakable, fragile little balloons, we are going to put this big, heavy piece of plywood, and you guys are going to help me with this. So I need one person kind of behind the podium there, and one person on my side. So that's Chloe, and I forgot your name. And Robert. Okay, we're going to give one end to Robert. Chloe's going to pick up the other end, and I'm just back over here because I have balloon issues. And you're going to put that big, heavy plywood board and just squash the living daylights out of those balloons in it. Oh. They're not breaking. That's a bit of a relief. Why aren't they breaking? If we drop them, would they break? Why aren't they breaking? Okay, so we're distributing. If I stood on it with one high-heeled shoe, a balloon would pop for sure. If I spread out the pressure or the force over a much bigger area, then each balloon's only taking a little bit of the weight. There's another thing that's going on here. That's kind of the explanation for the bed of nails, but there's another thing that's going on with balloons. They're very stretchy. You can stretch a balloon quite a lot if you don't manage to rip it. Okay, don't go away. I need you. I need you. I need these two gentlemen here in the second row. Convenient of you to be here. Awesome. And what are your names? Anouk. Okay. Anouk. And? Say it. And Sunder? Okay. So Anouk and Sunder are going to come up here, and they are going to be our first guinea pigs for the new sport, the Olympic sport of balloon surfing. So for beginners, I am going to ask that you not attempt to move the surfboard very far. Is that cool? Okay, so our helpers, remember I have balloon issues, so I can be up here. Our helpers are just going to make sure the balloons stay underneath, and because we're kind of on a precipice, they're going to make sure that nobody falls off. Okay, so come on up for a second. Stand right in the middle of that there, caterpillar. Okay, now, you know what? I think people would like to see your smiling face, so turn yourself around very carefully. Look at that, it holds its weight. Now, you guys aren't actually lifting that at all, are you? No, just steadying it? Yeah, okay, good. Okay, Anouk is going to come up and join what I might assume might be his brother. Okay? So hang on to each other, guys, because it's a bit unsteady up there. Turn around. Oh, it holds two kids. You guys got the exact count of those balloons, right? No, they did. There's about 15 balloons. All right, I need some more people. Oh, sure, come on up. Come on up. All right, this is your new helper. And we're going to just scoot you guys a little bit to the sides. There we go, and come on up. I'm positive. And you're going to... Yeah, we're gonna let the guys be part of the team here, so you're gonna have to hold on to the belts. Oh, 3 up balloon surfing. All right, who else would like to try balloon surfing in the blue there? All right. Go. Is anybody curious? I mean, besides that, when it's gonna pop? Okay, scooch over, and John is gonna join us. Oh. 4 people balloon surfing. All right. 2 people's in red. They tell me they didn't have enough jobs to do. Okay. Now, how are we going to get you guys on? How will go in between the last person and the second one in and a bit in front? So my 2 teacher types will have to shoot back, and my 2 kid types will have to shoot forward a bit. Okay. Balloon surfing. Okay, let's have got somebody with one more person with really tiny feet. One more tiny feet person. One more time. Oh, willing to come up? And one dad. That's you. You're my dad. Back there. Come on up. Oh yeah, come on up. I have 8. Okay, snuggle up.
I'm going to get in front of Mark.
Now it's going to work.
13 balloons. Okay, come on up. No. Okay, make sure your feet are on the thing there. Hang on to the kids there. All right. Hands up, everybody. Make sure you don't hold up. Give my whole church a big round of applause.
Wow, that was amazing. We'd like to thank on behalf of the BC Science executives, Sandy, for doing a wonderful presentation.